one of the application of derivative is to look at what's so-called rate of change. And rate of change here, as a matter of fact, rate of change, we don't have to wait until calculus to hear about it because we've learned about rate of change like long ago, right? So the idea of rate of change is like this. So you got a function, say up and down, right? And so there's a, let's say for this function f of x right here, to give you a point A, for example, right? And then there's a point B right here. So on the interval, on the x-axis, we have an interval from A to B right here. So right here at x equals A, right? When x equals A, we have a point on the graph right here. At that point, you see, I can quickly draw this height right here. This height, right? That vertical height right here. That is f of A. You guys agree with me, okay? Right. That vertical height, right? Where see, we substitute A into the function right here. And so on the graph, we have a point, and that point stays vertically at the value being f of A. And so similarly, when x equals B, right, at the end of that interval, so once again, substituting that into the function, we have another point on the graph, right? And so that point here on the graph has another height right here. And so that height there, yes, we can call that height right here f of B. You guys with me on that, okay? But so now you've learned from your earlier days that in that way, how you see the graph, there's always a change, there's always a difference between the f of A and f of B, right? I'm not saying that f of B has to be higher or f of A has to be higher, but there's always a difference in the vertical value, right? In the output values of them. See what I'm saying now? And so in that way, there's a change, right? There's a difference, there's a change in the vertical values, and also there's a change in the x values on the x-axis, because the interval itself is already indicating a change, right? Okay, so right here I call that see the vertical arrow over here is indicating the change, right? The change in y value, and then from A to B right here. Okay. That distance between the 2 points in our interval, yes, we can call that as a change in x. Okay, so we've got a change in x, we've got a change in y, and so in that way right here, from our pre-calculus 1 learning, we've learned that we can just simply put the change in y value, right, over the change in the x value right here. That famous ratio here, yes, we call that as the rate of change, right? It's the rate of change. And now precisely, now we're talking about the rate of change for our function on, limited to this function right here. So it's rate of change of our function f of x. That's how we've been knowing it. See what I'm saying, no? And then changing y over changing x right here, a lot of times people refer to this with some shorthand symbol. So changing y right here, people calling that it's some delta y, right? Delta is a Greek letter D, a Greek capital letter D that stands for difference. See what I'm saying? That, right? So delta y is for changing y, and then so here changing x, we can also call it delta x. And so that's why sometimes a lot of textbooks out there use the symbol delta y over delta x as a ratio. That's indicating a change. See what I'm saying, no? Okay. And then think about it. Now, graphically speaking, if we're connecting the 2 points, you can see again the idea is the interval on the x-axis here represents that we change the x value, the x input from some x equals A to some x equals B. That's why there's a change in x. And then as there's some change in x inputs, right, the function's value comes out being changed as well. See what I'm saying? The function changed accordingly. And so in that way, now connecting the 2 points here from x equals A to x equals B right here, right? We end up with some kind of line connecting through the 2 points, right? And please forgive my drawing with that, right? But that line connecting through the 2 points on our graph right here, this change in y over changing x right here, that rate of change right there is indeed exactly the slope of that line there, right? But that line that I'm drawing here is only a secant. You guys following me on that? And then more precisely speaking, see See the changing y, yes, that's more like the general fundamental. For example, the changing y or the delta y precisely, it is what? Final f value, which is f of b, right? And final, I mean the function value at the final point in our interval, right? At the final end. And then final f value minus initial f value, which is f of a. And then we divide by final x value minus initial x value, b minus a. That's why there are so many ways of writing it, right? But it's all one famous formula for the rate of change we've been learning. See what I'm saying there? And so with this kind of understanding, we have been able to do a lot of problems already. And this is even before calculus stuff. This is nothing calculus yet. So think about, in some daily application, think about we can have a graph like this. Think about the vertical axis here is to represent your position. So position is some kind of capital P of t here, right? And then time is on this horizontal axis here. And so it's what it say here with this graph, and I don't even have to tell you what that graph is. I don't even have to tell you the function. Let's say the graph comes out something like this. So what it says is that as time goes by steadily, right? As time going, so think about when t equals 0, you may be like at home, right? And then as you walk to school like this, right? And your positions keep changing. See what I'm saying? Like you keep gaining more position and more positions, okay? And so, and then maybe position may sound a little too much with physics involved right there. Then we can just think about the p right here is to be the distance that you travel, the distance that you got away from home right there. Okay, just in one direction. Here is your home at time 0 that you started, right? So time equals 0 here, and as time goes by, you're walking to school, you're making more distance. So yeah, let's switch that p instead of position. Let's call p right here to represent distance. How's that? Right? And that's the closest understanding right there. So every day we walk to school, right? And so right at the starting time, when time equals 0, starting time, and you're at home. So, and then you're walking away, okay? And then so you gain more distance. So the vertical value here on the graph means you gain more distance. You get more distance. See what I'm saying there? Okay. And so in that way, right there, at sometimes a to sometimes b, right? You got an interval again. Right? At sometimes a to sometimes b, you got an interval. And see there's substituting a and b into our function p of t. This point right here, the height, right? We call it as p of a. You guys follow it? Right? And then this height here, that represents the distance that you have gained, right? How much distance you have reached when time is b, so it's p of b. But then there's always a famous difference between the two vertical height right here. Yes? I call that. This is the change. Now in this particular setup right here, it's the change in what? Change in distance. Because yes, it's a change of a function value, but we're talking about the change in distance, right? How much distance you have changed over the time from A to time B. And then there's a total time elapsed right here. You guys following? Right? Yes? Mathematically we call it as a change in time, right? It's a change in time, but then really it's just the amount of time elapsed. You guys following? Okay. And so in that way, think about it. I just want to bring in some daily application that you guys see it. So again, as a rate of change, right? And we put that change in distance, right? The change of distance over, meaning how much distance you have gained with that, right? Over the change in time as a ratio. So yes, we call that the rate of change for the distance function right here, but in a more daily term, what do you guys recognize this as? It's the speed, right? And it's not like we don't even have to go to college algebra to know what speed is, right? They've been teaching like the elementary school students that, hey, speed is how much distance over time, see what I'm saying? But now a little more precisely, right? How much change in distance over changing time, see what I'm saying? So yes, speed is one of the concepts, the daily concept we've been using, right? So commonly with that. But it's behind the scene, it is the rate of change of a function. If we consider the speed, as, I mean, if we consider distance as a function, right? And time as the input variable, and so the speed is the rate of change. So yes, right there is speed, right? The rate of change of the distance p, right? Now, a little more precisely in the interval from A to B, you guys follow me on that? So the kind of rate of change that we do it. So let me get back to this board right here. And I can add in that extra detail here. So rate of change, yes, it's the rate of change of the function, but even more precisely, it's in an interval from A to B, right? We've got to have an interval. That's the kind of rate of change we've been looking at. So just in that way, and I'm going to keep getting back and putting in some more important understanding. Our function f of x, right? Function. Calculate the rate of change. Rate of change of two intervals, 0, 1, and another interval, 1 calculation. Okay. So the work here is quite simple. Here's how I'm seeing it. We've got a given interval, right? Being specified here. We are required to calculate the rate of change, right? So the formula is still here on the board. We have, see, this is going to be our actual formula anytime that we want to calculate the rate of change for any function. Okay. And so in that way, getting into this problem here. Now the first interval, our starting point, our initial x value is here, right? Initial input is here, final input is there. So rate of change can be done pretty quickly, right? Rate of change, then here going to be a little more precise, right? Over that interval from 0 to 1, right? So how do we calculate that? The function value at the final point, right? Subtract the function value at the initial point, at the initial end of our interval with them, and we divide it by final x minus initial x. Okay. Sounds good? Changing y or changing x. The difference in the y value, subtracting the difference in the x value. So in that way right here, yes, that rate of change came out being, and by the way, we have to now substitute it and calculate, right? So that's giving me, and in the denominator, it's just simply 1, so that's easy for the later step. Here I'm looking at 1 squared minus 3 times 1, right, in parentheses, and we're subtracting, again, the same function, but I'm substituting in x equals 0, right? So we got 0 squared minus 3 times 0, right? And that should be easy enough to all 0 out, right? So our value here comes out being a negative 2. You guys all agree? I hope I'm not moving too fast. So this entire example for now is just triggering up your or bringing back your skill in calculating rate of change. So another repeated word here. How about rate of change, right? Rate of change over the interval from 1 to 3. You guys following? The way we're calculating it, we need to go f of 3, right? So it's all about, we get the final point, the final value, right? Meaning the final output value at that, the final point of the interval. Subtract the initial point, the initial value at the initial point of our interval. We are dividing that by 3 minus 1. Right? Now this one here takes us into some more calculation. We need to go 3 squared minus 3 times 3, right, in parentheses. Good with that, okay? And we're subtracting, and now we're looking at 1 whole squared minus 3 times 1, right? And we divide that by 2. You guys following? So that here gives me, okay, that's a 0, isn't it? Right? That's a 9 minus 9, that's giving me a 0, that's a negative 2. Negative 2, but with a 2 right here. You good with that still? Right? It's a negative 2 altogether here, but divided by a 2, yeah, so it's going to make it a positive 1. So let's quickly demonstrate through the picture of that. I was saying earlier, the tangent line, I mean the rate of change is just simply the slope of that line if you connect that line between the 2 points indicating the change again, right? So let me bring that into the picture again. Okay, so here's our function. Put it in f of x again, right? And then I get this x squared minus 3x. You guys all agree? Okay. Now, in the picture right here, the interval from 0 to 1, let me zoom it in. See, the interval from 0 to 1 is here on the x-axis. That's 0 to 1. You guys are all good with me on that, Victor? And so now you can see that, so clearly let me put it in a little bit. See, you got 0 comma f of 0 pops out a point, right there. This is the initial point on the graph. And then we have another point right here. How about 1 comma f of 1, right? We got another point. It's right here, popped out just now in green. How about, let me change the color. Right, so you got 2 points there, right in your picture. And so now if I connect these two lines right here, I mean if I connect these two right here, right? That line in blue just now pop out, and you don't even need to worry about how I can come up with the line so quickly like that. But the idea that if we're connecting the two lines, I mean if we're connecting the 2 points right here, the rate of change we have calculated earlier on the board was -2, right? That is exactly consistent with the slope of this line connecting the 2 points right here in that interval being a -2. Okay, and so similarly, now I'm going to put in the other point. So from 1 to 3, 1 is here, we already had a point here, right? 1 to 3. So when x equals 3, we have a point right here. You guys see where my mouse cursor is at right there? Okay, so let's put in that point. Okay, so you can go the 3 comma f of 3 right there, right? We got a point right there. Once again, let's put that in blue ink. So the line, the earlier line, we got it in purple, and now let's put in that line right there, right? How about, right? Okay, so this line in blue just now connects between the 2 points right there, right? And so that line here, you can see that this line connects between this point and that point. It's happening in between that interval from 1 to 3 right there. The slope for that line, that secant line, is what? Positive 1, right? 1 up over 1 run right there. And so now it's a little extra. It was not part of this example, but let me put in a little extra question right there, and then we're going to swing back to the graph one more time later on. What happened if I ask for, so in the same work there, okay? And hopefully you guys wrote down a good record of these work here. Rate of change over the interval from 0 to 3. How would we do that? F of 3, right? Minus f of 0. So doing that, right? And we're dividing that by 3 minus 0. Just the same exact formula, right? Like how we've done it earlier. The only thing I want you guys to notice is 0 to 3 is the big interval that has all these 2 sub-intervals inside of that. You guys see what I'm saying, no? Okay. The 1, I mean the 0 to 1 and the 1 to 3 are all the little sub-partitions of that bigger, longer interval. We good with that? So go ahead and take your time calculating that for me. The calculation should come out being what? 0. Okay. And so graphically speaking, it looks like this. Okay, so on the graph right here, for you guys to see, there you go. So just now, from 0 to 3, it's that interval over here. You guys following? Okay, so now I'm using a line that connects through those 2 points on the graph here. Then our line appears to be flat, right? It's a flat horizontal line right there. So slope 0. Sounds good. Slope 0, and that's consistent with our calculation that the rate of change being 0. So let me point out the situation. The idea now is that we want to learn a new terminology here. The idea now is that we got a graph, right? We got a graph. There's an interval, some start with the ending. That's how we have an interval, right? And then we calculated the rate of change in between that interval right there. Okay, we got some, but the idea is, see, I purposely brought in some small intervals and then some bigger interval that has both of these. The point I'm trying to make now is that even if, think about the interval from 0 to 3 right here. Let me kind of reorganize my picture. Think about right in our problem right here, from 0 to some 3, right? We got some kind of graph there. See what I'm saying? Right, that's not exactly the version of the real problem here, but from between 0 to 3, the point now is that if we make the interval smaller, like from 0 to 1 and from 1 to 3, we got all kinds of different slope right there going on, right? So there's this different slope in a smaller interval, and then in between 1 and 3, it's a different slope in between them. See what I'm saying? A different rate of change like that. So just an interval that you have right here, it's not a precise one. See what I'm saying? Because as you break that into smaller intervals, right? You got yours. rate of change value changes in the smaller subintervals, in each of the subintervals. And so the real precise term now is that the kind of rate of change you guys have been learning throughout the whole time so far, up to this point, throughout pre-calculus 1, we actually refer to them precisely as the average, okay? It's only called the average rate of change there because it's some kind of rate of change that kind of like average out after so many little intervals. Okay? After so many little subintervals. Okay? And so in that way I can come back to this board here and modify that wording. And so this kind of rate of change is we've been calculating with the formula that, and we need 2 points for this rate of change. It's strictly now called the average rate of change. Okay. So now you can see that when we're doing rate of change like that, it's not precise, right? Because as you break it down into subintervals, and you got all little rate of change and all happening differently. And so my question next is, what we want to know next is that, let me try to just simply retain the graph right here. Okay. So here's your function. It's been that line swinging up and down. Right? There's a function, f of x. Okay. The question arose here is that, can we find the rate of change? Find the rate of change. Let's say I put a point A right here, x equals A right here. Okay. Can we find the rate of change? But here's the thing: the requirement only at x equals A. You know what I'm saying that? That's the question. Right? The word to be highlighted here is we want to find the rate of change, but only at that value given x equals A. Because from what you have observed so far, yes, if you go from A to B, right, some B point right here, if you go from A to B, then you got the rate of change over an interval, right? We call it, it's the average rate of change, but it's clearly not precise. It's clearly not precise. So think about it, I brought up throughout example 1 that we've done earlier, that think about if we break that into smaller subintervals, think about instead of being that long for an interval, right? We make the interval smaller. How about from A to B is only here? Are you seeing what I'm trying to describe? Okay? We make the interval smaller into subintervals. So we still have an average rate of change because that's 2 points. You see what I'm saying? No? But that's not what I need. So no matter how small we break down the interval, we still in the end end up with just some average rate of change happening between that noticeable interval. But now I want, precisely speaking, I want to find the rate of change, right? Only at that thing right here. That means the idea now is that I will keep bringing B closer and closer to that point A right there. I will keep bringing B closer to that point A. So between B and A, right? And now really I have to make the picture a little cleaner between B and A right here. That's that space right here we call that the distance h. You guys follow it? Right? There's that distance h right here. And so yes, f of B is A plus h. F of A, yes, the initial point is just A, right? But f of B is now we understand that as A plus h. The distance between A and B, that's h, right? And then, like I was describing, I want the rate that happens only at x equals A. And so doing that, this is the rate, but over an interval. So to get the rate only at A, I keep getting B closer to A. So that means that the h distance here keep getting smaller, right? It's the limit problem. You guys follow it? So now do you realize about that limit? What do you recognize about that limit setup right there? It is the slope of the tangent line, right? It is the slope of the tangent line, the famous slope of the tangent line we've been learning. So it's the tangent line the slope of the tangent line at x equals A on the graph right there. It means the rate of change but only happening at x equals A. Yes, and then truly, we've also learned that this is not only the slope of the tangent line, but it's the derivative, right, of the function at A right there as well. So that's the first reason that leads to one of the closest application about the slope of the tangent line. The slope of the tangent line now is no longer just one geometry problem, no longer just that. The slope of the tangent line means it's the rate of change, right? But only at that value given right there. Okay? And so now, rate of change only at x equals A. A little more precisely, we refer to that as See, this term here that I underline, I circle in red, okay, right? So we got a function and it's the rate of change. So more precisely, we call it it's an instantaneous it's instantaneous rate of change. See, the kind of rate of change that happens only at one instance. The next instance is going to change. Right? Right, so it's the instantaneous rate of change of f of x. Let's see. Now we're talking about precisely at x equals a. That's why I say, hey, rate of change only at x equals a, right, on that function. So only at that x equals a instance, we call it a instantaneous rate of change. And so now that's the meaning of derivative. Up to this point right here, derivative is the slope of the tangent line. The slope of the tangent line now really means in practical application, it's the rate of change, right, the instantaneous rate of change of f of x. And so we no longer need 2 points. We can just calculate that rate of change right at that point again, right? So, but now how about the same function here? Let's calculate the instantaneous, right? The instantaneous rate of change. So now part A, about at x equals 0. You guys can see that? And so truly, at this point, the instantaneous rate of change, I spent all of that time explaining, so now it's the real unlocking key is it's just the derivative of the function, right, at x equals 0. Okay. So in this case, here we're going to just, and at this point, you guys have learned so much technique in finding derivatives, so there's no reason to make you go through the limit definition anymore. You see what I'm saying? So that's just the plan, right? That's just the plan. We're first going to, so we write the plan there, and actually let me do that. That's just a help of the plan here. We're going to take the derivative. See what I'm saying there? And the derivative will come out easily just being 2x, right? Minus 3. Okay. So now in that way, right here, f prime of 0 will come out here just 2 times 0 minus 3. Okay. That's what you get. Negative 3. That's our instantaneous rate of change. The next part of the question. How about at x equals, I did 1, right? I got an interval from 1 to 3 as well, right? 0 to 1 and 1 to 3. So the f prime is already found being 2x minus 3 for the function. Just as a reminder. Now f prime of 1 equals 2 times 1 minus 3. That's the instantaneous rate of change. And that's making it minus 1. Good. And then the last, then I want to put in one more prop for that part C, I mean for that example. So how about at x equals 3? Right? So the same derivative, we can reuse it. And substituting x equals 3 in there, we're looking at 2 times 3 and minus 3. For part A, the answer was -1. For part C, the answer would be positive 3. You guys all good with me right there? Okay, I have a little task for you guys. It was not part of the problem with that, but so can you go ahead and you got the slope, right? And remember, the slope here is the slope of the tangent line, and it's been explained, right? The average rate, I mean the instantaneous rate of change is the slope of the tangent line. Am I correct? Okay, so I explained that. So now why don't you get the complete, because right now you already have the slope, right? Why don't you get the complete equation of tangent line at x equals 0 for me? Can you guys do that? Understanding my instruction right there? Get the complete equation. Get the equation of tangent line. Right? I can leave that for you to do independently. Right? At x equals 0 for that part A right there. And then for part B, once you're done with the slope, once again, I also need you to obtain independently, right? Sort of like for your triangle, right? Right? Equation of tangent line right? At x equals 1, right? And then I also want equation of tangent line, and it should be taking quick now. It should be quick, pretty fast. Tangent line, right? At x equals 3. Okay. I'm going to prepare the screen right now. All right, so it's time to have a look at that. 3 tension points right there, right, on our graph. Okay? Those are the 3 tension points on our graph. So now, for x equals 0, right here at that tension point, let's see if you guys agree with this, okay? See if you guys have come to the agreement with that. So, it's that line right there. Y equals negative 3x. You guys all agree? Okay, so you've reached some agreement. But so, what's my point of keep bringing up the tension line? So now, because we've been talking about instantaneous rate of change, right? So I'm talking now. You have to understand. Right, only at that instant. Think about if this point was moving along the curve here. See what I'm saying now? Think about as the x value changes steadily, right? Then the point here is going to be changing. The point is going to be changing on the graph, right? Through that path, that parabolic path. So only at that instance, when x equals 0, the point will keep falling down, right? At that slope being negative 3. You know what I'm saying now? But only at that instance. Okay? Because now, think about it. If you change to x equals some other x value other than x equals 0 right there, it's going to change to a different slope already. That's why it's called the instantaneous rate of change. Okay? And so now in that way, what did you guys find for your next one? See, now think about we changed the instant when x equals 1, for example. Okay? And then let me bring in the graph a little closer to everyone. Okay? So everyone can see here what the equation should be reading. So that's 1 comma negative 2, right? So it's going to be y plus 2, right, equals the slope we found was a negative 1. Okay? And then 1 minus 1 like that. You guys get that tension line with that? I mean, I was using point slope, but it should be another way of writing it. There you go. Did you guys agree with that line right there? Right? And then this is another line, and I can put a black ink right here. Okay? But once again, you can see that now we change from x equals 0 instant to x equals 1. So right at that instant where x equals 1, you see the line already changed its slope right there, right? And so the instantaneous rate of change also refers to sort of like a tendency where your point is going. You see what I'm saying? That's sort of like a tendency. But that tendency, even though it's a tendency, but immediately when we change to a different position, when we change to a different instant, it's already changed to a different tendency for direction. So right at that moment, right, it's tending to head down that way. So think about if you freeze time. It's a little abstract of a concept right here, but think about if you continue to move into the same pace, then the graph will not bend like that. Instead, the graph is going to go straight down. That's why it's called a tendency. Just think about if you keep changing, the rate of change keeps changing, but if you freeze that same rate of change, and starting at that moment, right, starting at that instant, and you freeze that, you keep that the rate of change the same, then the graph is going to continue heading down that way instead of bending up. Okay, that's the idea, right? So any of these that we calculated, yes, these are referred to now as just instantaneous rate of change, right, at x equals 0. This value here is the instantaneous rate of change of the function, right, at x equals 1. And the same way over here, this is the instantaneous rate of change of the function when x equals 3 at those different instances.